Hello class. Before starting nonlinear analysis, I would like to explain a few important points about this nonlinear behavior. Later it will be easier for us to understand what we are doing and what items we are manipulating when we are doing nonlinear analysis. So the main question is going to be what is nonlinear behavior? Okay, remember for finite element subject we start FEA with describing a spring, something like this, and I said we apply a force, and because of that force we are going to have a displacement which we use U as displacement, and also we had stiffness for K for that spring. And when we draw the displacement, and force diagram, it was something like this, linear, and I said this slope is going to be K, and we considered K constant number. So when we consider K is constant, all the relations are going to be linear, and based on that assumption we constructed a stiffness matrix and many more things we learned. And let me write the general formula we had. It was force equal stiffness matrix times displacement. Okay, and basically we just developed Hooke's law. Okay, what if we hadn't that constant K? So usually materials behave like this. If we had this case, we don't have a linear graph here. So if I draw the slope of this graph, for example here, let me draw this again. So if I draw a slope at this point, it is going to be like this. So K is going to slope of that line. Here it is going to be like this. So K is going to be variable. When K is variable, we are going to say this material is going to have nonlinear behavior. So if it's nonlinear and K is not constant number, it is going to create some trouble to construct stiffness matrix, and we need to update the stiffness matrix, depends on force or displacement we have. So how ANSYS is going to take care of this? ANSYS is going to take care of this nonlinear behavior by using linear relations and equations. So how many nonlinearities we are going to have? We are going to have three main sources of nonlinearities. So three main. The first one is going to be geometric nonlinearities. The second one is going to be material nonlinearities, and the third one is going to be contact. So what I mean when I say geometric nonlinearities, imagine you have a fishing rod. If you start stretching the fishing rod more than it can tolerate, it is going to show us some nonlinear behavior. If the material was nonlinear, it is going to show like a plastic deformation. It is going to be material nonlinearities. Or sometimes we have contacts. Two materials with different stiffness are in contact with each other, so stiffness from one material to another material is going to dramatically change. This sudden change of stiffness is going to also create nonlinearities. So it is going to be based on because of contact, because of material, and because of the load of forces applied, like a buckling. Remember, the buckling of the columns happens when we have elastic material, but the behavior or the forces applied causes nonlinear behavior. Okay. So what ANSYS does is creating iterative process and using linear approximation to solve this nonlinear behavior. So let's see what is going to ANSYS do for this case. So let me redraw here. This is our force and displacement graph, like this. So let's imagine this is our force A, which is going to fail. We shouldn't reach this FA, and corresponding displacement is going to be U. So ANSYS is going to start like this. Instead of using this curved graph, ANSYS is going to say, let's find a tangent here and draw a straight line. So ANSYS is going to linearly increase force to reach this point FA, which is going to the material supposed to fail, and then it is going to drop to this point. So from this point to this point, it is going to be one load cycle. Then again ANSYS is going to say, okay, another line again to the failure point, then come back. Second cycle, another line, come back. Third one, fourth one, now it is converged. So this is number 1, number 2, number 3, number 4. Number 4 almost converged, and we reached the K we want. So it is going to be an iterative process and based on linear approximation. This method called Newton rough method. When ANSYS increases up to FA and brings it back to, for example, this one is going to be F1, or the other one is going to be F2, and then F3, F4, the difference between FA and, for example, F1 is going to be residual. And ANSYS is going to try decrease the residual. If this residual decreases to a certain limits, we are going to consider we converged. If your ANSYS calculation this value of residual gradually increased, it is going to diverge, and it's going to show you failure or error message. So everything is all about this residual, and ANSYS is going to try decrease that residual. So how we can decrease this residual? It's not easy. You need to make sure your geometry is correct, your boundary conditions are correct, your mesh density is correct and fine enough, and also you need to check the number of sub-steps and maximum and minimum steps gradually to find. And if it's not enough, you need to gradually decrease the number of steps to converge. Basically, it's about trial and error. When you get more experience or you have more training, that trial and error time is going to decrease. I just told you, for example, about mesh. If you check other things and everything was okay, and still you were getting some errors regarding this divergence, you need to check the mesh option. For example, we have an option for mesh which is called shape checking. Usually we don't touch it, but if you have nonlinear model and it's diverges all the time and you did everything, you need to change this option to aggressive. So by changing this option to aggressive, ANSYS is going to make sure the quality of mesh is much better, and it's going to be anticipate the distortion of the elements we have, because we are supposed to have a large deflection, and when we have large deflection, those mesh are going to stretch and creates a lot of trouble and failure. So ANSYS is going to make sure we have better quality mesh, and sometimes it is going to work just with changing this. And you remember when we talked about strain. Let me write the formula for a strain. It was B matrix, strain displacement matrix, multiplied by displacement, nodal displacement. And we said, for example, if this is my element, we selected sampling points like this here, and then we start constructing strain displacement matrix, and finally stiffness matrix. And we use these lines to interpolate, these nodes to interpolate inside our element. So to improve the possibility of converging, you need to change one other option. Let me write it here. So this is our 3D element, and these are our nodes, and we have some nodes for example here at the center. So if you are doing nonlinear behavior analysis, we prefer to get rid of these mid-side nodes, because if the element is supposed to stretch and we have a large deflection, these extra nodes are going to create trouble for us, and there is an option for that inside advanced section of meshing. When you open mesh option, there is a option for element mid-side nodes, which you are going to select dropped. So it is going to automatically drop those nodes, which is going to decrease the possibility of this conflicts when you have large deflections. Yeah, so I don't have any other things to say. So it's mainly try and error. You need to get used to adjusting these options. Google it. Sometimes some people find better options. So just understanding what type of nonlinear behavior we are investigating, and you are going to see this convergence graph when you select when you solve ANSYS for nonlinear. You can change the monitoring option to force convergence, and it is going to ANSYS is going to show you the that graph, which is sometimes depends on the number of steps you have. It takes like 100, 200, 1000, 2000 sub steps to converge. Okay, it's enough fundamental information. Hope you use it, and if you find something interesting, go further, Google it and learn more. See you next time.